In this video, we're going to be talking about organic isomerism. So there are two different types of isomerism. One is constitutional isomerism, second is stereoisomerism. So as you all know, that constitutional isomerism refers to isomers of the same molecular formula but different structural formula, while stereoisomerism refers to organic molecules which have the same structural formula but different spatial formula. To recap on what spatial means, it's basically about the space where the atoms are at. So in a sense, whether is it at the into the page, out of the page, or whether is it it's basically the space where the atoms is at. So let's go for constitutional isomerism first. So there are three different types of constitutional isomerism. There's chain, positional, and functional isomerism. So for chain isomerism, right, it's about the different arrangement of the carbon atoms in the chain. So it can be a straight chain like butane, or it can be a branched chain like 2-methylpropane, where there's a methyl group sticking out in the second carbon. Then positional isomerism is basically where the atoms are being positioned that are arranged on different carbons. So it's more on like the functional groups mainly, but in this case, chlorine atom can be one group in a sense. So it's more of the different position of the substituents or the uh, functional groups. So for this case, 1-chloropropane and 2-chloropropane, the chlorines are at different carbon atoms. And then functional isomerism is basically how, if we remember that for some formulas, for some organic compounds, they have the same general formula. So for instance, cyclopropane and propene. So cyclopropane and propene, you know how alkenes, so alkenes and cycloalkanes, general formula is CnH2n. So in this case, they can form isomers. So there will be, you can have an isomer where prop one in, so there's a C double bond in the first carbon, which is the alkene group, or you can have it as a cycloalkane, so in a sense cyclopropane, where the three carbons are arranged in a closed chain. Okay, then there is also stereoisomerism. There is the cis-trans isomerism and the enantiomerism. So for cis-trans isomerism, to recap, it's basically the criteria for it to happen is that you need to have a restricted rotation about the C double bond C pi bond in the aliphatic alkene, or a C single bond C sigma bond in a small rigid ring. And the main thing to take note is that there must be two different groups in each of the carbon atom that is involved in the double bond. So as you can see for the first example, the aliphatic alkene. So in this aliphatic alkene, there's the C double bond C pi bond. Okay. And that there is two different groups bonded to each of the carbon atoms, bromine and hydrogen, and that's why cis-trans isomerism occurs. Okay, recap. Cis refers to same side, so basically, the identical groups will be placed at the same side of the double bond. So the two bromines are on top, two hydrogen below. Trans is identical groups on the opposite side, so it means bromine on top, one bromine below. Okay, the second example of a cis trans isomerism is a cycloalkene. So this cycloalkene, there's this C double bond C pi bond inside this a cyclic ring. So there's this cis cyclooctane and trans cyclooctane. So in this case, one important thing to note is that for cis trans isomerism in cycloalkenes, take note, cycloalkenes, right? So they must have 8 carbon atoms because of the geometrical constraints of a double bond. So about the geometrical constraint of a double bond, it means that if you have less than 7 carbon atoms, you only can have cis arrangement but not a trans arrangement. So in a trans arrangement, as you can see, if it's this case is a cyclohexene, okay? So cyclohexene, the cis exists but the trans does not, because as you can see, the trans ring is very strained. So it's not possible because of this geometrical constraints, and that's why it's only 8 carbon. So just one important note. And to draw the trans cyclooctane, if you want to make it easier, you just need to know it's like in a figure 8. So just go one round. There's in a sense 2 hexagons. So there's these 2 hexagons shape that are there. So I can draw for y'all to make it easier. So there's this one. There's a double bond here. Then you have one hydrogen on top, one hydrogen below. Then draw a what you call that, a hexagon on top, another hexagon. So this is 1, 2, 3, another hexagon below. Okay, so yeah, and then as you can see right here, if you count the number of atoms, yes, there is 8. So this one is the figure 8. So 1, 2, 3, 4, and this bond here is passing through. So then 5, 6, 7, 8. So this right here is just an overlap. It goes under the double bond. Alright, okay. Then there's cycloalkanes. Cycloalkanes, whereby there's a C double bond, C sigma bonds. So there will be the 2 hydrogen on top, the 2 chlorines at the bottom for cis arrangement, and then same goes for the trans. So it's in a sense, it's similar to like there's one on top, one below. So it's just um more of like one, like the chlorine is in front and the hydrogen is at the back, for instance. So, and then there's enantiomerism. So enantiomerism, all you need to know is that you need to have an asterisk sign on the carbon, and then there's a hash and wedge bonds. So the bolded bond is at the front, the other, the sort of, you call that the dash, this dash bond, right, is into the page, while this one is out of the page. Into page, out of page. Yeah. In this video, we're going to be talking about enantiomerism. So enantiomerism involves optically active chiral compounds, which exist as a pair of isomers called enantiomers. Okay, and then they rotate plane polarized light. So what plane polarized light means is that notice how light travels in all different directions. So light exists as a wave. Okay. Um, Yeah, light exists as a wave, and I'm gonna draw out light waves. So imagine this light wave that is in two directions, even though it's in many directions. So this is light in two directions, perpendicular to each other. Like the two light waves are perpendicular to each other. So this is the light waves coming out from the light source, from light source. And then when it passes through the fixed polarizer right here, this one, only one direction, it will only allow light to go through in one direction, which is the vertical direction. Okay, so if you do not know what this means in the polarizer diagram, this is the front view of your light wave particles. So this is the side view. Okay, and this shows the front view. So in a sense, your wave particle is oscillating up and down. Yeah, and then after passing through this polarizer, it will pass through the polarimeter tube, whereby it will whereby this polarimeter tube will contain an optically active substance. And this optically active substance will help to rotate the plane polarized light, whether clockwise or anti-clockwise. It will be shown in this analyzer. Yeah. Okay. That's all you need to know for plane polarized light. You do not need to memorize this. It's just need to know that it rotates plane polarized light. Okay. Then enantiomers also contain chiral carbon. So this chiral carbon have four different groups bonded to the carbon atom, as seen from bromochlorofluoromethane, whereby there's four different groups bonded to the carbon atom. Okay. Notice I'll talk about it later that not all optically active substance not all compounds that contains chiral carbon is optically active substance. We'll talk about it when I talk about meso compounds. So also just a warning that we do not accept like double bond and triple bonds because only three or two groups are bonded to the carbon atom, as seen from the example of ethanol chloride and ethane nitrile. Okay, then they also have non-superimposable mirror images. So if you see from this diagram, notice how these two notice how uh there's okay, let me change. Notice that these two chiral compounds, they are mirror images to each other, and the orange ball is in front, the purple ball is at the back, purple ball at the back, orange ball in front. But then if you rotate it in a certain way whereby your green ball and your red ball still remains at the same position, but on the opposite side, you realize that the purple ball and the orange ball switch directions. So the purple ball will be in front, but the orange ball will be at the back. Okay, so it's like imagine you rotate this molecule all the way until such that this green ball ends up here. Okay, and what you're gonna end up with is that this and this will be non-superimposable because they are not identical. Not identical. All right. If it's to illustrate, if it's superimposable, uh, and that is why I have to also say that four different groups four groups that are bonded to the carbon atom must be different. You cannot have uh even two atoms being of the same group, because if there was two atoms being of the same group bonded to the carbon atom, then you will realize that if you rotate this structure in the sense that the green ball will end up on the opposite side over here, then you realize that the purple balls will be uh will be in front of the will be on the right side of the molecule, which is the exact same as this compound right here. So this shows that it's identical and superimposable. So this wise is achiral. You can take this as an analogy whereby human hands, left hand and right hand, are mirror images of each other, and that's why you cannot these hands cannot be superimposed because they are not identical. Yeah. Also, just take note that there's no plane, axis, and center of symmetry. I'll tell you why when I go to meso compounds. Yeah, right here. So meso compounds, they have two or more chiral centers, but they themselves are optically inactive and achiral. They contain an internal plane of symmetry, whereby half of the molecule is a mirror image of the other half of the molecule. So one example here is tartaric acid. So in tartaric acid, right, notice there is these two chiral carbons, one at the top, one at the bottom. The top and the bottom side, they are symmetrical to each other. That's why there's this internal plane of symmetry. And then you notice if we take for instance that the top chiral carbon rotate plane polarized light by minus 10 degrees, which is anticlockwise, and the bottom chiral carbon rotate plane polarized light by plus 10 degrees clockwise. So because they are in different direction but the same magnitude, that's why your net rotation of plane polarized light by this entire meso tartaric acid is 0 degrees, and thus this is why meso compounds are optically inactive, even though they contain chiral centers. So that's why chiral centers, the presence of chiral centers in the molecule does not indicate that it is necessarily a chiral compound. What determines what determines whether a compound is chiral or not is whether it is able to be non-superimposable. Okay, whether it has non-superimposable mirror images. That's the most important criteria. As you can see here, this is just enantiomers of tartaric acid, whereby the top and bottom, there is no internal plane of symmetry, and because of that, it has two chiral carbons that help to rotate plane polarized light by the same direction and the same magnitude, and that causes a net rotation of that is not zero, and that's why it's optically active and chiral. Then next up, number of stereoisomers. This is the formula, so it's just 2 to the power of n, where by n is the number of stereocenters, whether it be C double bond C or chiral carbon. And an example to illustrate this is that imagine like your first if there's the first carbon double bond carbon, there's cis and trans, okay? So for every cis and trans, oopsies, for every cis and trans molecule, there will also be another set of cis and trans. As you can see right here, there will be one more set and one more set. And this continues on for the third C double bond C. Okay? Yeah, so in a sense, for every single carbon, double bond carbon, and chiral carbon, there will always be two isomers. So it's two stereoisomers. So it will just keep on going. Yeah. Okay, let's do this example. Alright. To mark out, I already mark out the chiral carbons for you. So it's just to take note, is to look out for any Y shapes in the compound and avoid any V shapes. So to convince you all why to look out for Y shapes and to avoid V shapes, I'll tell you about example V shapes right here. So if imagine this one here. So there's this V shape, and then notice this is a skeletal structure, so it would mean that there is two hydrogen that we ignored. So in a sense, for every V, there will be these two hydrogen atoms right here, and that's why there's no for that's why because there's only there's two hydrogen there, so it does not have four different groups bonded to that carbon, and that's why you have to avoid all the V shapes. Okay, then for Y shapes, right? Take for instance this. It is bonded to a methyl group. It is bonded to this group right here, whereby the next carbon that is bonded to is bonded to oxygen that has a double bond. So this is one, this is two, this. So then you come to this two. So you notice how for this two, the next carbon that is bonded to is this one. This is the third one. So maybe this one's that is just a V shape, so it will be something like this. So this group 3 is looks something like this, and then continues on forward, and then group 4 it will look something like this. So you notice how group 3 and group 4 are very different. So that's how you can determine which compound is chiral or not. Okay. Okay, let's take a look at the example of isomers of pentene. So pentene is a C5H10. So you have draw out the longest chain, 1, 2, 3, 4, 5, and then surround, and then it's a double bond because it's an alkene, and then fill the rest with hydrogen. Okay, so in this one, we can represent this in a skeletal formula. So in this case, it will look like this. Alright. Alright, okay. Then another isomer we can think about is positional isomers. So we can change the position of the C double bond O, sorry, C double bond C, and this will form you another isomer, which is number 2. If you're thinking of moving this isomer to the third one, it would be the same as number 2. So this one is wrong. This one is wrong. Okay. If you're gonna move it at the last one, it will be the same as this, so it will be wrong also. Okay. Alright. Now what is your next step if you ran out of all the positional isomer for 5 carbon? So what you want to do is to go down to the next smaller alkene, which will be butene. So you have 4 carbons, and then you put the double bond at the first carbon. So what you're going to do now is to use chain isomerism to add one more chain here. Okay, so in this case there will be 1, 2, 3, 4, 5 carbons, and you'll still be a alkene, and there's no repeats at all because there's one chain sticking out at this side. Next one will be, if we keep the double bond at the first carbon, we can have another chain sticking out here. It will be a new isomer right here. Another thing we can think about, if we can't move the chain at the 4 carbon, at the 4 carbon, we can also move the functional group when the longest chain is butane. Okay, so if the longest chain is butane, sorry, my bad. If the longest chain is butene, we can still shift the functional group. So in this case, the functional group is on the first carbon. Now we can shift it to the second carbon. Okay, you can shift it to the second carbon, and then we can have another chain. So maybe on this chain, we can put it here. Okay, and this will be another new isomer. All right. If you're thinking about having another isomer, let's say if we still keep the double bond here, okay, if we still keep the double bond here, if we keep the double bond here and you think of adding a chain here, it will still be the same as this. You just rotate it in a certain way, rotate it anti-clockwise, and you'll get the same shape as number 5. Okay, so this one is wrong. So we cannot also shift the double bond to the last one, because in that case it will still be no matter how much you do, you still end up the same as, so this one will be the same as number 4 if you go change it about, and if you add one more chain here, it will be the same as number 3. So this one is out also. So if you cannot move the chain, you cannot move the position, what to do next? What we can do next, right, is to think about functional groups. Yeah, functional groups, isomerism. So functional group isomerism we can have is cyclopentene. Cyclopentene has 5 carbons. Cyclopentane, my bad, cyclopentane. Cyclopentane. And we can also have a methyl group sticking out of a butane, and that will be methyl cyclobutane. And we can also have an ethyl group right here, and an ethyl group will be this ethyl cyclopentane. Okay, another one that is possible is if you have 2 methyl groups. So in this case, we need to add you can also add the number here also, it's also fine. So 1 methyl, 1, yeah, you can also add the number, and then for this case is dimethyl, so you can have 1, 2 dimethyl cyclopentane. Yeah, so this is all the constitutional isomers. Yeah, and you must be thinking about stereoisomers. So cis trans, of all the molecules we look at the double bonds, because cis trans only exists in the double bond. 5 cannot because it have 2 methyl groups. 1 cannot because it has 2 hydrogen groups. 3 and 4 have 2 hydrogen atoms on the same carbon. So this carbon, and this carbon, they have 2 hydrogens atoms. And since there's 2 identical groups on the same, yeah, cis trans doesn't exist. This one is 2 CH3 groups. So that's why cannot. So only cis trans exists for this one, because there's a methyl group and a hydrogen group right here, and then there's an ethyl group and a hydrogen atom on the other carbon. We can draw out for this case. This one will be a trans, and this one and another one would be Oh, sorry, I'm drawing the same one. Okay, just flip it the other way around, and then you get cis because the two hydrogens are uh on the same side of the double bond. Also notice that cis trans isomerism can also exist in cycloalkanes and cycloalkenes. So as you can see here, we have from organic molecules 6 to 9, you can see there's this the closed rings. So let's take a look at each of the closed ring and see whether cis trans isomerism do exist. So for compound 6, there is no cis-trans isomerism because each carbon is also bonded to 2 hydrogen. So in a sense, no cis-trans. Then for compound 7, each carbon is also bonded to 2 hydrogen. Only this carbon um, only this carbon uh, is bonded to a CH3 and a hydrogen. However, for cis-trans isomerism, if you treat this as the C sigma bond in the small rigid ring, then this one must also have 2 different groups. However, this one has 2 hydrogen atoms bonded to it. So this one no cis-trans. Okay. For compound 8, cis-trans does not exist because these two bonded to hydrogen atoms. This one is bonded to an alkene, sorry, an ethyl group and the hydrogen atom. So this one cis-trans does not exist. However, for compound 9, as you can see, if we treat this as the CC sigma ring, where the restricted rotation is about this, okay, it's not the ring, where the restricted rotation is about this CC sigma bond, then it can work because this one, there's 2 different groups, CH3 and a H. This one is a CH3 and a H. So if you were to draw out this molecule for cis-trans, it can exist. So 11, okay, so there will be a CH3 here and a H at the bottom, a CH3 here and a H at the bottom. Yep. And then for 12, there'll be another triangle. There'll be a CH3, H, H, and CH3. And this is trans. While this is, whereas this compound 11 is cis. Okay, so now what else we can consider is enantiomerism. So for the first 5 compounds, or sorry, the first 5 isomers, you can see that it's very hard for enantiomers to exist, especially when there's a double bond. So, and then for enantiomerism to exist, then must be a chiral carbon. However, compound 1, so isomer 1, isomer 2, isomer 3, isomer 4, and isomer 5 do not have chiral carbons. Okay, and that is because you don't really see any Y shapes. And one exclusion of Y shapes, it will be this one. This Y shape you can see there is two methyl groups being bonded to this Y shape. So this one in enantiomers does not exist as it's not a chiral carbon. Then for isomer 6 also cannot because each carbon already bonded to two hydrogens, so that's cannot. 7, you have a methyl group, you have a hydrogen in a sense at the bottom here, and then this carbon is bonded to, then you also have CH2, 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 and CH2, CH2, CH2. Whether you go this way or this way, you'll still get these two same groups. So that's why there's no chiral carbon for this molecule. For 8, also the same case because it's in a sense symmetrical. So that's why if you go this way or this way, even though there's, we have the ethyl group being bonded and the H also, there's one H here. However, if you go this way, like if you go in a clockwise, so if you go anti-clockwise, you'll realize you'll be bonded to this. And then if you go clockwise here, you realize it's bonded to CH2 and a CH2. So yeah, so no enantiomerism here. For 9, wise, you realize that hey, enantiomerism can occur because it's bonded to a methyl group, it's bonded to a hydrogen group. So there's a hydrogen here, and then if you go clockwise and clockwise and anti-clockwise, you realize in the clockwise direction you'll have CH3, and then you have CH2. You go in the anti-clockwise direction, it will be CH2, and then CH3. So you can see it's two different groups being bonded together, and that's why chiral carbon, this is a chiral carbon. This one, also the same thing, it's also another chiral carbon. Yeah. So in this case, we can draw out the enantiomers for 9, and I will draw it right here. Since there's 2 of them, alright. Okay, let's take a look at this isomer. So for this isomer, we have this chiral carbon. So since there's this chiral carbon, we're gonna just casually fill in the 4 different groups. So the 4 different groups, we start off with the methyl group, the hydrogen atom, and then there's a triangle surrounding the chiral carbon. So this triangle, we will draw it first, and we can have the top carbon to be a CH2, or the bottom carbon to have a methyl group and a hydrogen atom, as you can see right here. So there's a methyl group and a hydrogen atom. Since this carbon is also chiral, so and that's why we have the border and the dash. Okay, now next up we can look at we're just gonna copy this one but in the reverse order. Okay, now let's take a look at 15 and 16 because there's another chiral carbon over here, this one over here. So we're just gonna do the same thing as before, but now because recall that for every chiral carbon there will always be 2 enantiomers. So that's why we can have the hydrogen atom out of the page, while the methyl group will be into the page. Yes, and then we'll do the same for this, just that it's in the other, in a mirror image. Yep, and now we're gonna learn about hybridization. So first up, we need to understand when we are forming bonds such as covalent sigma bonds, we tend to assume that it's like we use the s orbitals and p orbitals. However, for some molecules, they require you to hybridize the atomic orbitals. So we all know that covalent sigma bond formation involves sharing half-filled orbitals. So in a sense, one atom shares one electron of one orbital, so it's and then another atom share one electron of an orbital, and that will give you a sigma bond. Alright, then however the ground state of carbon as you can see over here at the bottom, this ground state of carbon, it only has two half-filled orbitals, so it just means that you can only form two sigma bonds with carbon. But what we know is that carbon needs to form four of these bonds so that to achieve stable octet electronic configuration. So that's where we need hybridization so that we are able to form these four sigma bonds in carbon compounds. Okay, so let's take this for instance. I'm gonna talk about formation of sp3 orbitals. Afterwards, I'm gonna use an analogy to illustrate how these hybrid orbitals are being formed. So I'll do this for sp3, sp2, and sp. Okay, so for sp3 orbitals, firstly, there's the ground state electronic configuration of carbon. So if you heat it up, the electrons in the 2s orbital will absorb energy and excite to the next level, which is the 2p-Z orbital, and then it will be able to hybridize. So what it means by hybridize, it means that the 2s and the 2p orbitals will be able to mix and combine together to form. So it's a mixing and combining of 2s and 2p orbitals to form sp3 orbitals. So we are gonna use one 2s orbital and 3 of these 2p orbitals in order to form 4 sp3 hybrid orbitals. Okay, the tool right here is to suggest that this is at the quantum energy level of 2. So it's the second electron shell in the atom. Okay. Don't get what is that called? Don't get intimidated by sp3. sp3 is meaning that it has 25% s character and 75% p character, meaning it is formed from one s orbital and 3 p orbital. So whenever you form sp3 hybrid orbitals, there can only be 4 of the orbitals. There is no such thing as 3 sp3 or 2 sp3. Okay, so this is for forming sp3 hybrid orbitals, and all these electrons that you see right here, these are now half filled, and then they can be used to form the 4 sigma bonds. Okay, and then I use an analogy. This analogy is the fruit punch analogy. So imagine you have invited 4 friends, okay, and you want to uh treat them a certain drink. Okay, so you decided to make your own type of drink. All right, so at home you have 1 strawberry juice and 3 papaya juice. Your friends all of your 4 friends want to taste your newly made fruit punch. Okay, so what you decided to do is to mix 1 strawberry juice and 3 papaya juice. Okay, and this will be able to help you make you 4 of the fruit punches for your 4 of your friends. So each fruit punch will be able to contain 3 papaya juices, 3 cups of papaya juices and 1 cup of strawberry juice. So that is in a sense a mixture. Okay, so imagine your strawberry juice as your 2s orbital and your papaya juice as 2p orbital. Okay, so that's how you are able to get 75% papaya and 25% strawberry. In a sense, it's formed from 1 strawberry juice and 3 papaya juice. And we can say this one is the sp3 orbital. Moving on, sp2. So sp2, now what you want to do, you excite already, is excite the electron from 2s to 2p. Now you decided that because for for sp2 orbitals, just to inform y'all, is can be found in molecules like ethene. So whereby there is a double bond here. Okay, so because there's this double bond, you know that double bond there it contains 1 sigma and 1 pi. Yeah, 1 sigma and 1 pi bond. So you know that pi bonds, it can only be formed between your two, it can be only be formed between your p orbitals. So you want to make sure that one of your orbitals is unhybridized, and then if you know that one of their orbitals is unhybridized, then you'll be able to mix the rest of the orbitals. So you'll be able to mix 1 2s orbital and 2 2p orbitals. Okay, so once you mix these orbitals, you'll be able to form sp2 now. Alright, so instead of this manner of presentation, it will be 3 sp2 hybrid orbitals and 1 unhybridized 2pz orbital. Alright, so So yeah, that is how you'll be able to form the sp2 hybrid orbitals, and these three of these sp2 hybrid orbitals, it will be able to help you form your 3 sigma bonds. So 1 sigma bond with your hydrogen, 1 sigma bond with your another hydrogen, and 1 sigma bond with your carbon. And then the one unhybridized 2pz orbital will be used to form your pi bond between the other carbon, and that's how the double bond will arise. Okay, sp2, it will be around 66%. Sorry, not 66, 33.3, and then the other one will be around 66.6 p character. So 33.3 s character, 66% p character, and it will be formed from 1 s and 2 p orbitals. Okay, now if you're gonna go back to our fruit punch analogy, so imagine now one of your friend is actually allergic to strawberry juice. So since one out of your 4 friends are allergic to one of your 4 friends is allergic to strawberry juice. So in this case, um you know what, we decide that we should reserve this one for your friend who is allergic to strawberry juice, so that okay, at least he drink papaya juice, he won't have any major injuries. So and then you decided, okay, we're gonna mix 1 strawberry juice and the other 2 papaya juices. So you mix them and you'll be able to form your fruit punch, and you give this fruit punch containing 2 papaya juices and 1 strawberry juice to 3 of your friends only. So only 3 of your friends will get this special fruit punch. However, it will now contain 66% papaya and 33% strawberry. Alright, and then this papaya juice is gonna be just reserved for your allergic friend. So it will be in a sense unhybridized. It's like the unhybridized 2pz orbital. Okay, so yeah, that's for sp2, and then sp is, in a sense, if you're gonna have, instead of ethene, you have ethine, so it will be a triple bond. So in a triple bond, you have 1 sigma with, if you consider this carbon right here, it will form 1 sigma bond with a hydrogen, and it will form 2 pi bonds with your other carbon and 1 sigma bond. So you can see there's 2 bond pairs for this 1 carbon right here. So what you're gonna do, if you want to, there's this 2 pi bonds they need to form, and so you will know that we're gonna have these 2 being unhybridized. So these 2 being unhybridized, it will mean that you have also an unhybridized 2py orbital right here. Okay, so getting the hybridized orbitals out of the way, and then you have only 1 2s and 1 2p orbital left that you can mix and combine. And this, when you do the hybridization, it will help you form uh sp orbital. Okay, it will help you form your sp orbital. So it now becomes sp. Alright, so sp now, as you can see, there's only 2 of the sp orbitals. So 2 of the sp hybrid orbitals. Okay, Yeah, and then how you gonna apply this to our ethine is that these two of these sp hybrid orbitals, they'll be used to help you form this sigma bond. So this sigma bonds will be your sp, and then your hybrid orbital will be your unhybridized orbital will be your pi bond. All right. Okay, yeah, and then going back to the fruit punch, now it's like imagining both of your friends, two friends out of your four friends are allergic to strawberry juice. So if in that case you want to reserve your papaya juice, and then you just only mix one of the strawberry juice and one of the papaya juice to help you form two of the fruit punch to give to two of your friends who are not allergic. In such a way, right? So just one papaya juice, and this one will be your two papaya juices reserved for your friend, and those will represent your unhybridized 2p orbitals. Okay, and then the fruit punch is will be now 50% papaya, 50% strawberry. So in the same way, your sp orbital now will be just 50%, will be now 50% S and 50% P character. And instead of, so now it's just one S and one P orbital that is being formed. So don't be intimidated by the name. It's just the SP, SP2, and SP3 is just the name of the hybrid orbitals. Okay. Now we can move on to identifying the types of hybridization in molecules. So if just to summarize everything, right? If four of the atoms are directly bonded to the carbon, as you can see here, this is your ethane molecule. Ethane molecule. Um, you realize each carbon there's four bond pairs, or in a sense, four sigma bonds surrounding it. So in a sense, you need four sigma bonds. If you know that you need four of these sigma bonds, you will realize that you need four hybrid orbitals. And thinking back, four hybrid orbitals, it will always be sp3, because sp3 is always four hybrid orbitals. Okay, then if three atoms are bonded together, so in a sense three bond pairs, um, whereby in this ethene you have three sigma and one pi. So you want to form these three sigma bonds, right? You would have three hybrid orbitals. And then same goes for the sp, because there's two sigma bonds, two pi bonds, two sigma bonds. So it's just two hybrid orbitals, and that's how you get your sp. Okay. Um, other than carbon atoms, you can also there's also other atoms whereby you can there's also other atoms whereby you can actually also hybridize the atomic orbitals. So example, nitrogen and oxygen, they are also possible. So two of these hybridization rules you all need to take note of um in case questions ask you about the hybridization, uh to draw out the full orbital diagram of any compound involving oxygen, nitrogen that are being bonded to other atoms, right? Um, just take note, you need to take note of the steric number, which is the number of hybrid orbitals to be formed. As you can see here, the number of atoms bonded to the is equals to the number of atom bonded to the atom and the number of lone pairs. Uh, what I would think about it is that you think about how many hybrid orbitals you need to form for that um, atom that you are looking at, and then you take note of how many bond pairs and lone pairs are there. Okay, I will demonstrate an example to help you illustrate later. Then the second rule is that if the atom is a terminal atom, you do not hybridize. If it's if it has a single bond. Okay, so we take a look. If the steric number is 4 and that means it's sp3 because you will need 4 hybrid orbitals to form in the atom. And then the electronic geometry will be tetrahedral, and it's not the same thing as the shape of a molecule, because if you can see in ammonia right here, even though the shape is like the trigonal pyramidal, but as you can see, if you take into account all the electron pairs, the arrangement of the electron pairs, it looks like a tetrahedral arrangement. So as long if you see molecules that have the electronic arrangement in a tetrahedral arrangement, so all these this one bond, the one lone pair and the 3 bond pairs are arranged in a tetrahedral arrangement, then you will know that you need to hybridize your atomic orbitals to make them sp3 hybridized orbitals. Okay. Yeah, and another thing, since there's one lone pair plus 3 bond pairs, which gives you 4, and this is the steric number. Yeah, that's how you derive the steric number. And if you can see all the hydrogen, um, the orbitals that they use for the bonding, that they use to form the sigma bonds with the nitrogen, those are 1s orbitals. Those are 1s orbitals, so they do not hybridize. Okay. Alright, so if you're taking a look at the nitrogen atom, for instance, the ground state of nitrogen atoms is as shown here, and then the hybridized, we can see we are gonna mix all the 4 orbitals. So we're gonna mix 1 2s orbital and 3 2p orbitals, because as we discussed, we want to form sp3. So if we want to form sp3, we will form sp3 in this manner. We mix all 4 of these orbitals so that we can form your sp3 orbitals, and you can see there's 4 of these sp3 orbitals. There's this, and hence this lone pair will be used for here. Yeah, and then there's the 3 bond pairs that we need to form. You see, these are half-filled orbitals, and this will be used to form 3 sigma bonds with your 3 hydrogen atoms. Another example is your water also. So water, as you can see here, there's 2 lone pairs plus 2 bond pairs, and your steric number will be 4, and that's why you need to form your sp3 orbitals. So if you want to form sp3, you form it right here. So 1 2s and 3 2p will give you your 4 2 sp3 orbitals, and you can see right here that the 2 lone pairs that is shown right here in the sp3, we can use them to form the lone pairs as you see in this figure. So in this figure, yeah, it's a band shaped molecule, but it's a tetrahedral arrangement. When you're talking about the electron pairs being arranged, it's in a tetrahedral arrangement. Then the 2 leftover half-filled orbitals can be used to form your 2 sigma bonds with your 2 hydrogen atoms. Okay, so in a sense, this is how you do the this is 2 examples that you can look at. One misconception, I guess, is that you do not assume that if it's a lone pair, you do not assume that if it's a lone pair, it must be unhybridized. Okay, so in a sense, these 2 lone pairs right here, right, is sp3. Yeah. And this is because we are looking at the steric number and the electronic geometry of the the arrangement of all the electron pairs, and that's how we are able to determine. So whenever, yeah, so in a sense, whenever you are talking about what type of hybridized orbitals to form, you always take a look at the steric number and the electronic geometry of the molecule in a sense. So for sp3 is steric number 3. So sp2 is steric number 3, and in a sense you need 3 hybrid orbitals. Is trigonal planar arrangement for, in a sense, the electron pairs, and this is one molecule that you can look at. So we can take a look at the hydrogen and the chlorine first. Remember the rule number 2. Rule number 2 is about you do not hybridize the terminal atoms that are single bonded. So as you can see, H and Cl are terminal atoms, single bonded, so you do not hybridize. So this is one s orbital that's going to be used for your sigma bond formation with carbon, and then your chlorine is it will be your 3pz orbital to form your sigma bond with carbon. Yeah, so must be wondering, this one is also a terminal atom. However, this one is double bonded, so in a sense you still have to hybridize the orbitals of O atom. And also another, the fact that it's double bond, so you also need to form a pi bond. So there is a sigma bond formation and pi bond formation, so that's why you need to have the hybridization. So if we take a look at carbon first, alright? So carbon is the same concept as I mentioned just now. You just heat up, excite, and then hybridize. You get the 4 sp, sorry, you get the 2 sp2, sorry, you get the 3 of the sp2 hybrid orbitals, and then you reserve one of the 2p z orbitals to be unhybridized. So unhybridized so that you can form your 1 pi bond with your oxygen, and then 3 sigma bonds, and then your 3 of the hybrid sp2 orbitals you can be used to form your 3 sigma bonds with oxygen, hydrogen, and chlorine. Okay, so then oxygen wise, you excite, hybridize, and then you form 3 of the sp2 orbitals. So 2 of the sp2 orbitals, since they are lone pair, you can see right over here, there's actually 2 lone pairs right here for oxygen. And then the one of the half-filled orbitals, we're going to use that to form a sigma bond with carbon. So 1 sigma and 1 pi. Alright, then this unhybridized, it will be used to form your pi bond with your carbon. Okay, so yeah, then this is how the full orbital diagram of the molecule will look like. So you can see this is, okay, this is oxygen right here. This is oxygen. I'm not sure the cursor sees it, but this is oxygen. So oxygen has these 2 lone pairs. These 2 lone pairs are not in hybridized orbitals. They are in your sp2 orbitals. Okay, and then you have one of your sp2 orbitals of oxygen forming a sigma bond with the sp2 orbital of your carbon right here. Okay, and then there's the 2pz unhybridized orbital that you will form your pi bond with your carbon. Carbon also have an unhybridized 2pz orbital, and then you would have carbon whereby you have your whereby you have one of your sp2 orbitals you form sigma bond with your oxygen, then another sigma bond you form with your 1s orbital of your hydrogen atom, and then form another sigma bond with a 3pz orbital of your chlorine atom. So yeah, that's how it will look like. A bit complicated, but yes. Alright, the last one, this one was the steric number 2 for sp. You will need to have 2 hybrid orbitals, and the electronic geometry is linear in shape. So as you can see right here, like before, there's 2 bond pairs but no lone pair for carbon if you're gonna treat carbon. So 2 bond pairs, 2 lone pairs. This one will be steric number 4. Oh, sorry, no, there's no lone pair. What am I talking about? There's 0 lone pairs. So their steric number is 2. So that's why you have to form sp orbitals. Okay, another reason why you need to form sp orbitals, you look at the electron pair arrangement, it's in a linear shape. Since there's no lone electron pairs. So yes, that's why you need to form sp. Alright. The fact that sp is only 2 hybrid orbitals. So we take, for instance, carbon atom right here. If we're gonna, like as usual, excite and hybridize, and then you'll see that sp, there's only 2 sp hybrid orbitals, and these 2 sp hybrid orbitals are gonna be used to help, because these are half filled. We're gonna use them to form 2 sigma bonds with 2 oxygen atoms. So 2 sigma bonds right here with your oxygen atoms, and then 2py and 2pz, they will be unhybridized, reserved to be unhybridized, and then form 2 pi bonds with your 2 oxygen atom. So this is how you figure out the identify the hybridization for carbon atom in carbon dioxide. Okay, yeah, hybridization. That's all for hybridization. It's initially a complicated topic for me, but if you have any question, do feel free to ask me. Alright, thank you and have a nice day.